So last class, we fully defined our zigzag product. Right, there's some constraints on which two graphs you can take the product of, but once you satisfied those constraints, it was a pretty generic thing. And we started analyzing the spectral properties of zigzag product. Okay. And towards that end, we stated a theorem controlling the second largest eigenvalue of the zigzag product of two graphs. Okay. And as I said, you should basically think of zigzag product as doing something like this. It reduces the degree of G to be that of H, while the spectral gap is going to be close to both of them. Okay, so in some sense, if both are good, the new graph will also have reasonable spectral gap. Okay. All right. So today, what we'll do is to finish the analysis of zigzag, and then we'll see the applications to undercharacteristic connectivity and something called expander graphs. Okay, so those two are goals today. Okay, and before going on, couple of announcements. One, for everyone registered on Bruin Learn, you must have received some notification to register on the Gradescope for the class. If not, please register for it. And the reason I'm telling you now is on January 30 at 6 p.m. Right, 6 p.m. is in the evening. 30th is a Thursday. Okay, so I'll release the first homework / midterm. Okay, so this will be the first homework / midterm, and you will have 48 hours to submit it. Okay, it's really like a take-home exam. It'll cover material from the first, it's supposed to be 6, but now first 5 lectures until today. Okay, so mainly on zigzag product and so on. And you're free to ask questions about it on EdSTEM, but if you're revealing too much, then just make it a private question. Otherwise, you can, if it's just a clarification thing, just post it on EdSTEM. Okay, don't say, is this solution correct, and post your solution. Okay. All right. Any questions about the format of how this is going to go? Yeah. It's open book. You can do whatever you want. And it won't be too, sometimes take-home exam can be scary. It's like really problems might be really hard or something. But I don't think they are like that. Some of them are kind of stuff that I want you to just test your understanding of. Some of them are kind of based on maybe some lemma in some paper somewhere that I saw or wrote, things like that. Okay. All right. And I think it's worth 30 credits. Yeah, 30 points. Okay. And it will be released on Gradescope at that time, and you'll submit on Gradescope again by Saturday. So this is Thursday to Friday, Friday to Saturday. So Saturday at 6 p.m. again. Okay. All right. So just keep that in mind. So this is first 5 lectures. Okay. How long is the exam expected to take? It depends. If you definitely follow all the material so far, it should take something like a good, like let's say 2 assignments put together, right? So we don't have any assignments for this class. We just have the 3 exams. So typically, if you expect a class to have 6 assignments, then it's like 2 assignments put together. Okay. All right. So that's in terms of the announcements, and let's get on with where we were. Okay. So where were we? Okay. So we had this linear algebra lemmas, and what was the main claim that we were trying to prove? This one. Right? So this is what we were trying to prove, that when you take a zigzag product of two graphs, you can control the second largest eigenvalue, lambda of the new graph based on the lambdas of G and H. Okay. So in particular, you should think of lambda being 0 as the best case scenario. That doesn't usually happen. In fact, it never happens. It'll be very close to 0, but not quite 0. But let's say it's exactly 0. Then what are you getting? The new graph is also 0. Okay. But remember, the degree of this graph only depends on the degree of H. So in some sense, maybe it's not a better graph than G in terms of lambda, but it's going to be a better graph than G when you take the degree into account. Okay. So this lambda could be worse, meaning higher than lambda G or lambda H, but the point is that its degree only depends on H. Okay, that's what we're going to use, right? And towards this end, we also had a couple of lemmas which were important. So let's take this one first. Actually, not that one. This one. Right, so zigzag product seems like a complicated operation. It is. But when you look at it linear algebraically, somehow I think it looks simpler, right? So we don't exactly know what the adjacency matrix is if entry by entry, or what the normalized adjacency matrix is, but we have this nice product representation of what the graph is. Okay. And the last thing that we did, which is was kind of show some approximation of this matrix MF. Okay. So I think I'm going to just summarize what we had. Based on the expressions that we had from last lecture, we can write this matrix MF as 1 minus lambda H all squared times okay, so this is the sort of main term that we were left with. And then we had the error term, right? Plus some error term where the norm of the error term was at most this much. Okay, so this is what we ended up showing in towards the end of last lecture, right? Okay, so we used all these lemmas, and then eventually we had this error term, and the norm of this error term was at most this much. Okay. Again, this looks like a complicated expression like what we have here, but there is a way to interpret it somewhat intuitively. Okay. Can anyone guess what's a good interpretation of this? So let's look at what this matrix JD is. I want to stress this one so that you have a sense of what it means for a graph to have very small lambda, right? So what is JD? JD by D is a normalized adjacency kind of thing. Okay. What is this matrix? It's a D by D matrix, and all of the entries are just 1 over D. Okay. Now, what is the rank of this matrix? 1. What's the spectrum? What are the eigenvalues of this matrix? 1 and 0s, right? So this is the spectrum of JD by D. Okay. So this is in some sense the best graph we can hope for in terms of lambda, right? So what is the lambda of this graph? The second largest eigenvalue is 0. Second largest eigenvalue in absolute value. I mean, it has to be at least 0 because it's non-negative, and it is exactly 0. Okay. If you think of it as a graph, what it's saying is this is the, this is kind of like the adjacency matrix of the graph where I have d vertices, right? And what graph would you get? This vertex will be adjacent to everything, right? So it's the complete graph. The fully connected graph. You cannot get a graph which is better connected than this graph. Right? So one way to interpret this statement is, if you look here, we had MH, right? So MH is not necessarily the fully connected graph. Okay, it has a smaller degree than D. But we are able to kind of replace MH with this JD over D, which is our ideal graph, but we are gaining some error. We're gaining this sort of mitigating factor, 1 minus lambda h whole square. And then there is an error term, which again depends on lambda h. Okay. So if lambda h is 0, just like for JD over D, you would get exact representation here, which makes sense. Like the only graph which has lambda being 0 is this complete graph where everything is connected to everything. Okay. So that's one way to interpret it. Like, when you have small lambda, you're essentially trying to say that my graph behaves like the complete graph. That's the ideal approximation we should get. Okay. All right. Okay. So let's keep that sort of interpretation in our minds. And now that interpretation actually helps us with the rest of the combinatorics. Okay. And what's the rest of the combinatorics? The last thing that we need, again, is really we kind of luck out again in some sense by finding that there's a very simple expression for a complicated looking thing. Okay. So what do I mean by that? We have this term here. Now this depends on G. So far, we haven't used anything about G. We've only been working in some sense with what the spectral gap or what the lambda of H is. But now we have G showing up. But this PG is in between, and then you have this complicated tensor product. So what do you do with it? Okay. So here's the next claim. Oh, okay. Actually, you know what? I just remembered something. So someone pointed this out on EdStem. I'm glad that they did. But yeah, so I made a mistake in the definition of zigzag. Okay, where did it go? Okay, this edge label is fine, but where is the rotation map? Here. Okay. So this rotation map, I actually made a mistake here. This should have been I prime comma I double prime comma, right? So the way to interpret it is, if you traverse these edges, you should go back, right? So B prime is the I double primed neighbor of B. So you go there, and then you go back. And then if I take the I primed neighbor, I end up at A. Okay. So the K2 comma K1 is when you have consistent labeling. Otherwise, if you have consistent labeling for H, then I double prime equals K2 and I prime equals K1. But otherwise, you should use these things. Okay. This was a mistake that I had in the pseudocode yesterday. It doesn't change anything about the graph. But if you don't have consistent labeling, this is the exact thing to use. Okay. All right. Okay. So now, what is the other thing that happens very cleanly for us? Well, it's the following. So we are looking at this matrix. Okay. So let's get a sense of what this matrix looks like. Let me put this 1/d up front, just 1/d squared. Okay. What does this matrix look like? IN tensor JD. So if I write it in this block form, what would that matrix be like? Is the tensor of identity with essentially the all ones matrix. So I would just have all ones on here and zeros on the off diagonal pieces, right? So that's what tensor product does. So you would get 0, 0, 0, and just ones here. Okay, so this is what identity times the JD matrix is. Okay, now then we have the PG matrix in between. Which is also with permutation matrix, as we said, okay, this was the definition of the PG matrix. It's a permutation matrix, which is basically representing the rotation map of the graph G. Okay. And so just as we could interpret zigzag product as this product of three things, just to figure out or guess what the final matrix is going to look at, what can we do? We can also interpret this thing as a zigzag product of the complete graph with G, right? So again, this is only for sort of, so one way to interpret this matrix is G tensor, sorry, zigzag with complete graph, right? Complete graph meaning this matrix, this graph, okay? We can verify this independently, but I think it's helpful to just have this picture once. Okay, so for 4 vertices, for example, this would be the complete graph, right? So I would take G, right? And what should I get? I should take every hop here and then jump across clouds and then any hop here, right? So I'm saying this matrix, this product corresponds to the zigzag product of G zigzag with the complete graph, right? Now, what kind of edges would I expect? So if G was, let's say, we had this guy. So okay, so instead of just this cycle, we now have the complete graph with self loops, of course. Okay, so you would put self loops too. And that's the graph we are starting out with, and then we have to connect things, right? So for example, we have an edge from this cloud to this cloud, right? So what would happen in terms of the new graph in the zigzag product? Any guesses? How would these two clouds be connected? So I would take a jump and then go across and then do this, right? But what else should happen? So because you have the complete graph here, once I land in the other cloud, by taking the different edges, I would be connected to everything in that cloud. Okay. So for instance, let's say, I'm here, right? And this is the vertex 1 cloud. So this is 1, A. Now if I'm here, I take edge label A, so I end up, now maybe I go here. If this is a within cloud step, now I do the across cloud step. Where does B take me? Diagonally across, 1, 2, 3, 4, 5. Okay. After landing here, I would have edges to all of the vertices, right? So because of this, what ends up happening is in the new final graph, I would really have this vertex connected to everything here. All of these edges would show up because I can change the second label, right? I had to change the second label. And whenever I change the second label, I get connections to all of these things. Right? Okay. In the same way, if you just draw the edges, what happens is you'll end up getting sort of like this complete edges between these copies. Okay. And if you play around with these things, a bit more carefully, what you end up with is basically a vertex in cloud 1 is connected to every vertex in cloud, let's say 1, 2, 3, 4, 5, 6. Okay. So if you play around with this properly, what you get is, so remember the number of these blocks corresponds to the number of vertices in G, right? And within each, we have like the H thing. So the final product will actually just be the 1 over D squared that we have. And okay, so what do I mean here? Whenever there's an edge in G, there is an edge in G here, right? So that's why we were connecting these two clouds. Okay. If there is an edge in these, in G, those clouds will be completely connected to each other. Okay. In the final graph, it's not just that, earlier we had maybe one edge, two edges, but because we're putting complete graph in the cloud, these two things will be completely connected to each other. Okay. So if you think of it that way, so whenever there is an edge between two vertices in G, that entire block becomes all ones. So this complicated looking thing, this tensor product, again simplifies to something very nice. It's just AG tensor JD. Okay, meaning you're replacing every sort of non-zero entry in the matrix A, adjacency matrix of G, with the complete sort of all ones block. Okay. You just had to verify it entry by entry. This kind of shows at least that this is happening. So let's check some, let's say why this one would be connected. Okay, so if I'm here, this is 1, A, B, C, D. Okay. This one would be connected because I can take this as my first inter-cloud hop. And once I get there, it determines which cloud I go to next. Right? I would once again take this green edge. And after that, I have all of these edges. Okay? So I would still get the same thing, that this is connected to all 4. Okay? So lots of edges are getting thrown now. In the end, what you get is AG tensor J. A very simple representation. Okay? So you're putting sort of complete connections between clouds. Right? Okay. So what do we have now? What's the progress that we've made? Let's keep track of that. So the progress that we've made is the adjacency, normalized adjacency matrix, or the final thing that we were looking at, can now be written as MG tensor JD plus an error term. Okay. Okay, now we are basically done. We just have to use our linear algebra claim, linear algebra lemma 2, I think. Where did it go? Not lemma 2, but lemma 1. Yeah, this one. We already used it once. We're going to use it again. Okay, so this is what we had. I'm going to use it and say, okay, I can substitute mg equals 1 minus lambda g times jn by n plus lambda times E5, let's say, where the norm of E5 is less than or equal to 1. Okay. Plug this into our expression, we get MF is all right. And we put these things kind of, let me simplify this. So I have 1 minus lambda h all squared, 1 minus lambda g, jn tensor jd by n. Oh, okay, there's a d squared here, right? So it's, it should be by d here. I guess I get by nd plus, and this is some seemingly painful bookkeeping, but we are basically done except for the bookkeeping. Okay, any questions about this simplification? I just plugged in the two things together. And what can you tell me about this matrix? So this is the all ones matrix of size n, tensored with the all ones matrix of size d. What matrix would I get then? All ones of nd, right? So this is exactly 1 minus lambda h whole squared times 1 minus lambda g times j nd divided by nd. Okay. And then I have final term, like, let me call it E, where is at most 1 minus lambda h whole squared times this should be lambda g, right? Plus what was the norm of E4? 1 minus 1 minus lambda. Right? Because we know that this term has spectral norm 1 and that term has spectral norm at most something by the claim. So because norm of A plus B is at most norm of A plus norm of B, we get this inequality. Okay. And this we can simplify. This is 1 minus okay. Okay. So what's the summary? So if F was this zigzag product, what you just showed is that I can write down MF as okay. Now I claim we are done because of lemma 1 now, right? So remember, this whole thing is an if and only if statement. If I can write the normalized adjacency matrix as 1 minus lambda times j n by n plus lambda times e, then I know that the second largest eigenvalue is at most lambda. Okay, and that's exactly what we have here, right? So let me call this number as our final lambda or something. Okay, then what are we saying? We're saying I can write mf as 1 minus lambda times j nd by nd plus e, where this norm of E is at most lambda. Okay, which is exactly what we want. There's no magic that this 1 minus lambda h square, 1 minus lambda j, everything just fits perfectly, that you got lambda and 1 minus lambda and so on. That because approximations can be exact. That's the reason why it works. Okay, so now, so therefore, by lemma 1, the only if part, we can say that f is Okay. Which is what we wanted to show. Any questions about this? So the two key steps are first finding a nice representation for F, and then noticing that, the lemma 1 basically allows us to approximate the adjacency matrix with the all ones matrix, which is usually much, much easier, plus some error term where how much error you're getting is controlled by the second largest eigenvalue of that graph. Okay. So the second largest eigenvalue is very small. In some sense, it's saying I can approximate my graph or behave as if the graph is a complete graph, but I'll incur some error. The error can be controlled. Okay. All right. So the final zigzag theorem that we're going to use, and is very useful across many, many different contexts, is the following. So G is a n d lambda G graph. H is a d d1 lambda H graph. Then the zigzag product is a graph with more vertices, n times d. The degree only depends on the degree of H, and the spectral gap can be controlled in some sense. Okay, so this only depends on the degree of H. That's important. Question? Yeah. That's a very good question. So it is kind of almost sharp. You can find examples where it's the case, but people have also figured out that if I have some more control on G and H, like maybe not just the second largest eigenvalue, I have more information about the spectrum of H, then I can get even better bounds and so on. Okay. So I said, like, for instance, if lambda G and lambda H are 0, the new graph will also be very good. It's also 0. All right. Okay, so now let's see how to use this. The first application is going to be to get our undirected ST connectivity algorithm. And since it's been a little while, let me review it and where we got stuck and what led us on this sort of rabbit hole of second largest eigenvalue. Okay. So just to recall, what's our goal? We are given as input some graph G, a source vertex S, a target vertex T. G is an undirected graph. And our goal is to check are S comma T connected, right? And the main idea that we were using was that if every connected component of G has degree D, second largest eigenvalue less than or equal to lambda, okay, then we had this algorithm which was basically path enumeration. Check all paths of a certain length. If you hit T in that length, then you're happy. Otherwise, you say I'm not connected. Okay. Then we can solve ST connectivity in space, which was O of log of the degree times log of n. Okay, so this was where we were, a couple of lectures ago. And we said, okay, it's easy to bring down the degree starting from any graph. We said, okay, I can assume somehow at least that the degree is 4 to begin with, but then I don't have enough control on lambda. That could still be big, or so this number could still be quite large. Okay. All right. So what are we going to do now? We're going to use zigzag to improve the connectivity or improve the lambda of each connected component. Okay. We have to be a bit careful in terms of how we set up the parameters, but other than that, the idea is the following. We're going to take a fixed graph H, okay? And the graph will have certain number of vertices, some degree, and lambda H is at most 3/4. Again, this 3/4 is arbitrary. This B is also somewhat arbitrary. Basically, whatever the smallest graph that you can find where lambda is 3/4, that's what I'm interested in. Okay. And you can find these things like, on 16 vertices or something, you can do brute force search or their explicit constructions. You can do whatever you want for that because it's such a small graph. Okay. And you have to only find it once. There's a fixed graph. That's all we need. Okay. All right. And step 1. is I'm going to convert the input, the original input, GST. So we're trying to solve this problem, right? I'm given a graph G, S, comma, T. I'm going to convert this into G0, S0, T0. Okay. So we already saw that, given any graph, I can reduce the ST connectivity problem to ST connectivity on a graph where the graph had degree 4. Okay. Because I could do degree 4, I can also do other degrees. I can just add self loops if necessary. But just to be less tied down to the number 4, I'm going to say G0 is a B squared regular. Okay. So maybe instead of 4, I set it to be 16 regular graph. That's okay. Even if it has self loops, it's fine. I just need the regularity to be true initially. Okay. So let's say B was 4, then I have some number of vertices, and now I have 16 regular graphs. Right? So why am I doing this? The idea is that, I want to do this so the consistency condition of zigzag is easily met, and then I can just sort of run through with it. Okay. And phase 2 is where I'm going to push some things under the rug. What am I going to push under the rug? The main idea is something that we already discussed, but the details, how you code it up in pseudocode, are a little bit hairy, but it's not something too complicated. But that's not something I want to spend too much time on. Because there you have to talk about how I'm managing the list. I need to make sure my memory implementation is the right one. Okay. Okay. So what's the second step? For a certain number of steps, I'm going to do the following. So this G0 is a graph which has constant degree, 16 regular. Okay. But its lambda could be very bad. Right? So if this was 16 regular, in some sense, I already won here in terms of log t. But if I apply just the path enumeration, I might get terrible bounds because lambda is very high. Okay. So how do I improve this? We saw one operation which always improves the spectral gap, which was squaring the graph, right? If I square the graph, in some sense, the lambda becomes lambda squared. So I'm basically making this a half, right? If I decrease the denominator, then this whole thing is becoming a half, right? So there's a lot of progress, but earlier squaring also doubled or squared the degree. So the first term log of that became double. So the net gain was 0. Okay. So what can I do to mitigate that? So let's say I do G0 square to improve the lambda. But now what happened? I started with degree, like, B was 4. I started with degree 16, and then I end up with 64. Okay. So what can I do to bring the degree back down? I can do a zigzag with h, right? So let's check if it makes sense. So G0 square is a n, and what's its degree? B squared, sorry, b to the 4. Graph, right? So its degree is b to the 4. G0 is b squared. So when I square the graph, the degree also squares. I get b4. Okay. And the only consistency constraint that we have for taking zigzag is the degree of the first graph should match the number of vertices in the second graph, which is why we chose S and H in this way. Okay. So I take zigzag with H, and this is a b to the 4, comma b graph. Okay. And then I take the zigzag of these two. What do I get? What is the final graph going to be? How many vertices will it have? It will have, n times b to the 4. But what's the degree? Well, the degree should be the square of the degree of h. Okay. So I once again get a b squared graph. Right? So I'm kind of coming back to b squared regular always. Okay. So this is the operation again and again. Right? So the number of vertices every time you do gets multiplied by b to the 4. So I get this. Okay. I square the graph, improve the expansion, increase the degree. Then I do it zigzag with h, which might hurt the expansion a little bit, but it brings back the degree, and keep on repeating this again and again. Okay. So in the end, if I do this L times, so what is GL going to be? So number of vertices is pretty big, is n times okay. So every time I do the zigzag, I kind of blow up the number of vertices, right? Because every cloud, every vertex gets replaced with a small cloud. Do it again, every vertex gets replaced with a small cloud, and so on. Okay. And what's the degree of GL is not bad. So even though the number of vertices increase, the degree is still kind of just b squared. Okay. Maybe let me just state it for everything in between so that, right? Okay. So we're almost done, except we need to figure out how to kind of, where does this recursion lead us to, right? So this is step 2, and you have to compute all of these things. And the final step, of course, is solve ST connectivity on GL, SL, TL. Okay. So what do I mean by this? So you keep doing this operation of squaring, zigzag, squaring, zigzag, squaring, zigzag. You do this L times, you end up with some new graph, and you are going to solve ST connectivity on this new graph. But from which start and which source, which starting vertex and which target, you keep track of where our S0 and T0 go to. Where do they go? Oh yeah, here. Right, so we started out with these two things. Okay. So when I apply the first zigzag, this vertex gets expanded into a cloud. This vertex gets expanded into a cloud, right? You just keep track of, S1, T1 can be any vertices in these two clouds. Now you repeat the same thing again. This vertex gets expanded into a cloud. This vertex gets expanded into a cloud. You just keep track of, one vertex in these clouds, and that's fine. How do you keep track? You just have to write down the representation. Like in some sense, every expansion is like I'm adding one extra bit of representation to what the vertex is. Okay. You have to tell me which vertex in G0 and then which copy in H. Right. And then next time also is the same thing. Tell me which vertex in the first one and then which sub-vertex in the cloud. Okay. So it is possible to do that bookkeeping. Okay. In some sense, maybe let me just say a remark. Vertices in GK are really something like okay. So you're just adding sort of one extra, one potential reference within a cloud every time you do this operation. Okay. So SL could just be, the original thing, S0, and then whatever sequence you want. Anything in the cloud is okay. Right? I can, for example, just take 1, 1, 1, 1 or whatever. Doesn't quite matter. All right. Solve this thing using path enumeration. All right. Now, how much memory would step 3 take? Okay. So this kind of, one big question is whether or not you can actually do the zigzag operation in small space, but you can. That's just like, as I said, if you go to the rotation map, the definition of the pseudocodal rotation map, from those things, it's clear that you can actually implement it in small space. Okay. Maybe let me just flash that for a second. So where is the rotation map? Yeah. So imagine I have access to G and H. If they can be implemented in small space, you can ensure that this new one also can be implemented in small space. Right? You do one step, the second step, third step. The only thing you need to keep track of some additive things which correspond to which labels you used, and then you reuse. Okay. You need to make sure that your code optimizes for space, but it's not something that's too difficult to do. Right? Okay. So how much memory does the step 3 enumeration take? Well, it's going to take log of the degree times log of number of vertices in GL, I guess, and 1 over lambda. Okay. Now, what is the degree? we already said the degree is just b squared at every time. And the number of vertices is whatever you started out with times b to the 4l, and then you have 1 over. Okay, so b is a constant. As I said, you can actually take it like 4 or something else, you know. So that is fine. So this is just O of 1. And then you have log n 1 over lambda l plus log. Okay, there's a question by Mohan. How do you implement step 2 in a memory efficient way? It's a good question. So basically, you don't implement step 2 directly. What you implement is to do path enumeration. What you really need is to be able to compute the rotation map of GL. I give you an edge label. You have to tell me where would I end up at. Okay. So how do I do that? I need to compute the rotation map of like something like this. So okay, suppose someone gave me right? The degree is just is always b squared, right? The degree of g is still b squared. Okay. So I need to compute this. And now you go through each of the steps, step 1, step 2, step 3, and figure out. So the main thing that you really need to do is how do I compute so assuming we have rotation map of GL minus 1, this pseudocode is space efficient. Okay, so assuming we can already compute the rotation map of GL minus 1 space efficiently, we can do that for GL. Okay, in some sense, it's a little bit recursive, but you have to make sure that you do the recursion with some space efficient constraints, but it's not that difficult to do. Okay, so you have to go back to the pseudocode and say, okay, which of the, I need to implement these steps. First one is just like a step in H, so it's somewhat easy. And then I have to do this guy, but this, G is like GL minus 1 whole squared, right? So you need to make sure that I can use the calls for GL minus 1 efficiently and so on. Okay. It is not immediate. It requires some work, but it requires work which is kind of a little bit different from what we're trying to do, right? Basically, like you have to be very careful. It's like some lead code problem. You have to make sure that you're doing it space efficiently. But right now, let's focus on the big idea, which is what did we gain by doing this zigzag and doing this lambda? Okay. So this is the bound. Okay. Now this is O of 1 times log of n plus O of 1 times okay. So it all depends on what this lambda L is. This should be 1. Okay. All right. So what does lambda L look like? Well, let's see what happens to each time, right? So we have GK is GK minus 1 squared, zigzag H. So let's say lambda k is second largest eigenvalue of gk. Okay. If we know this, then what do we get, for instance? So if I apply zigzag, it's going to be lambda 1 is at most 1 minus lambda h whole squared times 1 minus lambda g0 squared. Okay, so this was the formula that we had from the analysis of zigzag. When you apply the zigzag product, the second largest eigenvalue is bounded by the lambdas of the corresponding graphs. Okay, but what is lambda of the square? Is just the square of lambda. Okay, and we chose h so that it is at most 1/4. So I can say this is 1 minus 3/4 whole squared times 1 minus lambda 0 squared. Okay, and you just have to do some arithmetic and you get some sort of recurrence relation. Okay, if lambda 0 is very close to 1, then you decrease it at a geometric rate. But if it's very close to 0, at some point you kind of bottom out. Okay, so in general, we have the recurrence relation lambda k is less than or equal to 1 minus 3/4 whole squared times 1 minus lambda k minus 1 squared. Okay, you can play around with this, simplify it a little bit and show that this implies that don't worry about where these numbers are coming from. Someone had to do the calculation for this recurrence. I did that, and you get something like this. Okay, don't worry. It's a little bit tedious, but not too fancy. You just have to work with it a little bit. Like, for example, what this means is I have 9/16 times 1 minus lambda k minus 1 squared is less than or equal to 1 minus lambda k. So I can write this as okay. And so, in some sense, if lambda k minus 1 is less than some number, then you improve it. Otherwise, you kind of do okay. Okay. But anyway, don't worry about the annoying arithmetic calculations, but in the end, you get something like this. Okay. And if I do further calculations using a calculator, you end up with the following. Some absolute constant. We will have okay. So at some point, you will actually take this, and that's all that you need. Okay. So the final arithmetic is tedious, but it's not magical. You just have to solve for this recurrence relation, and the punchline is that you basically improve lambda by a constant factor every time until it becomes smaller than a constant. So if like lambda is more than 0.9, then you decrease it by some constant factor. Once it gets below 0.9, you might not improve it, but we don't care. As long as it's not increasing and we're in that range of 0.9, we're happy. Okay. So now, if we go back to our thing, this would become O of 1. So when L is log of N0, we got lambda L is like 17 by 18, some constant. So this is just going to be log of N, which is N0 plus O of 1 times log N. Okay. You did the zigzag product, this operation, log N times, so that the lambda became a constant, and lambda became a constant. So both terms kind of balance out, and you get exactly O of log N. Okay. So eventually you get an algorithm which has space just log. All right. Any questions about this? So there are two things that we didn't go into depth. One is how to exactly implement this rotation map in log space. But as I said, it just means that you go through the pseudocode and write it in a space efficient way. Okay. The simplest way to do it, if I were to ask you to program it, you'll say I'll use recursion and just make two recursive calls, right? And that's pretty much what you need, except that you need to make sure that when you do the second recursive call, you don't have to, you can reuse the space from the first recursive call. Most programming languages kind of do it implicitly, but when I'm making two recursive calls, once I know the answer, that space that the first call used is free for me to reuse. Okay, so that's why it doesn't double. Space doesn't double, time can double. Okay. All right. And I also skipped this final calculations, but as I said, you just have to solve this recurrence relation, which is given by this guy. If I keep repeating something like this, where do you end up? And yeah. Like if it's 0.9, you keep on improving. If it's more than 0.9, you improve. And if it's less than 0.9, you're already done. Okay. Yeah. Oh, N0 was G0, like, the number of vertices.
Oh.
Okay. Yeah, that's a good point. I should just say N, in fact.
Yeah. Okay.
Yeah. Any other questions? Yeah.
So, like the 5.
Mm-hmm. It does, like, that's why we have this extra term, right? We did take that into account here, right? The cool thing about path enumeration is that the dependence in space, the number of vertices, is logarithmic, right? So that's what we are exploiting, really. Okay. Like the runtime does get a hit. The runtime is increasing by polynomial factor. Like, if L is like, 5 log n, then that's like, maybe n to the 20. Okay, but that's the crude thing. If you optimize it fully, you can make it almost like cubic or quadratic, maybe quartic algorithm. But the space would be maybe 10 times log. Okay, so we are sacrificing time, but gaining in space compared to breadth first search and depth first search. It's no longer linear time like those algorithms are, but those are linear space. We're getting making it exponentially more efficient in terms of space. Okay. All right. And if you can try writing down the pseudocode to be space efficient. If you have trouble with it, I can tell you, but I would say it's just more like, you have to just program it appropriately. There's no magic, but you just need to make sure that when I make this recursive calls, I reuse the space from the first one, and that's it. Okay. All right. Okay. And so as a final conclusion, I mean, this has been like 5 lectures in the making, right? So we started out with the basic definition of the problem, and now we do have a log space algorithm for connectivity in undirected graphs. Okay. And the key sort of things to take away are using spectrum to understand or to quantify connectivity. Right? And then using zigzag to improve spectrum. So improve just means that, I want the graph to be extremely well connected. Connectivity, the surrogate that we use is how large is the second largest eigenvalue. Okay. And there are actually some other very cool things that come out of this. I won't expand that, but I'll just state them. The first remark is there's something called universal traversal sequences. Okay, it's a very weird definition. Universal traversal sequences. Okay, so what are these things? These are determined by 2 things. One is let's say U T comma D is a collection of sequences of the form I1, I2 up to IT, where every element is a number from 1 through D. Okay. So it's like a path enumeration sequence, right? It's telling, okay, take, suppose I have a deregular graph, then the sequence tells you take edge number 1 out of my graph, out of where I am, then edge number 10, edge number 11, and so on. Okay. So this is just a sequence of edge labels to hop on from any vertex. Okay. So that's the interpretation. So it's a collection of sequences, and the way we'll interpret it is, if I have a deregular graph with edges labeled consistently, then the sequence gives me a path to follow. Okay. So just a collection of sequences. Now, what is a universal traversal sequence? Now these are indexed by the number of vertices and the degree. Okay. So un comma d, you should think of it as subset of d to the n. Okay, collection of n edges to follow. Okay, is universal if for any d-regular graph G on n vertices, and any vertices s comma t in G, there exists a sequence in un comma d that takes s to t. Okay, maybe let's say through t, it just passes through it. You can also do 2t if you just allow sequence of different lengths, but let's say it just goes through t. Okay, meaning it's like saying I have a set of instructions which is oblivious to the graph. It's oblivious to set of where you start and what you're targeting. But if I try all of the sequences here, I will hit t if there is a path. Any two connected vertices is coming. So it doesn't matter if the graph is graph can be anything on n vertices and d regular. Okay, it could have very long paths, that's okay, but even then one sequence from here will take you from s through t. Okay, these are called for any graph I can define traversal sequence because I can just look at, okay, maybe I follow these instructions, it's these instructions, and so on, right? It's like solving connectivity on all graphs at once, because I just have to follow some of these edge labels and I will get from S to T in any graph, no matter what the graph is, right? And one really remarkable consequence of there exists a not only there exists, but we can compute a universal traversal sequence where okay, there is a set of sequences which will work for any graph, any labeling, as long as it's consistent labeling, any start vertex, any target vertex, and the set is polynomial size, and you can actually compute it. Okay. So in some sense, it's saying connectivity seems like a hard problem, but there's just this fixed set of polynomial number of sequences. Try all of them, you're done. Okay, and just follows from, it's really implicit in this zigzag product. Basically, in the end, when you if you write down the pseudocode, you'll see that the final path enumeration only depends on labels in H, and you can use that to get this out. Okay. People knew that there exist sequences of polynomial length, but they did not know that you could compute it. And you can also compute it in a space efficient manner, which is also an interesting consequence, that you can compute, fact that it's computed in polynomial time is interesting, but even more than that, you can actually compute it in a space efficient manner, meaning given part of the sequence, I can tell you what the next element should be with only a small additional space. Okay. Now, universal travel sequences are really amazing. Okay. The fact that they exist and that we can compute them. All right. So that's one consequence of this whole construction. The other consequence is this notion of other construction is to the construction of some very special graphs. Okay. So to understand the definition of expander graphs, I mean, they were actually defined because someone wanted to prove some circuit lower bounds. But after that, people realized that they show up in so many places, in error correcting codes, in networking, in data structures, in pure math, in trying to do some metric embeddings, in operator algebra, and so on and so forth. Okay. But let's take the example of like, some kind of network you're trying to build, right? So what do I mean? So suppose I'm trying to connect, maybe I have n is like 10 to the 7, many different servers, okay? And I would like to connect all of them in some network. Okay, just say I want all of them to be connected with high bandwidth connections. Okay. So, if I want to lay these connections using, let's say, fiber optical cables or whatever, then there are other geographic constraints, but let's say the geographic constraints are similar in that they're kind of all equidistant to each other. The first thing you might try is I need a path between any two things, right? I need to be able to send a message from here all the way to anybody else, right? So the graph should be connected. Okay. And if you're trying to minimize the cost of laying down the network, then you would minimize the number of edges. Let's say trying to put one direct connection between them costs you $1 million. Okay. I mean, it's not unreal. Then I would say, okay, the first thing I would put is, what would the first sort of construction you would try? You're optimizing for money. You want to make sure that the network is fully connected, but you want to minimize how many edges you need to put down. What would you do? Yeah, just put a line through or something, okay? Degree 2, but it's like a path. All right. Now, this is good, but it has some severe drawbacks. What are some drawbacks? What are some important things that you need when you're trying to build a routing network? You don't want to have too much traffic. And they also have large latency here, right? The first and last have large latency. Okay, that's number one. Like, it looks good. It is connected, but the latency is very long, right? Okay, so the first problem is latency between first and second. Okay, so if you were to minimize, let's say I want to get around this, what would you do next? I need to reduce the longest, shortest path. Okay, that's the constraint. This is good because I've put down a few connections, like only n-1 edges, but then my latency is very bad. Yeah. I can connect the first and last nodes, but then what happens? It's cut in half, but half is still a bit long. Can I do better? Let's say I'm trying to trade off between how many edges I'm putting and kind of, the latency. We'll think of another important parameter in a second, but that's the main thing for now. What other sort of topology can I use to reduce the latency? Yeah. You can connect everything to one node, like the star graph, for example. Okay. Let's say, I have something here and, maybe but my claim is that this is also not a very good graph from a network perspective. Why? Yeah. Your fault tolerance is very bad, and the load that this one node takes is very high, right? So in some sense, this is what happens in our LAN networks, that you have a switch, which most of the things are connected to. So the switch has a very high load, but across switches or routers, you would like to balance them. Okay. So we don't want the load to be, so in terms of considerations, we want small latency to load. Basically, load is like the degree, right? How many connections do I have? Should be balanced. And fault tolerance also should be good. Okay. So let's say, let's not worry about 3, but let's say I want these 2 only. Load should be somewhat balanced, and fault tolerance, we'll think about that, but small latency, but these 2 things. What is one topology which satisfies these 2? So latency is kind of the longest, shortest path. So you want, things to be shorter, connected by short paths, and then load just means I don't want a single vertex to handle all of the responsibility. Right? So the degree should be small. There are graphs which satisfy this. For example, think of, we did draw one such graph. Right? What graph is this? This is the binary tree. Okay. If you take the binary tree graph, every vertex has small degree only 3, right? At most 3. And it's a tree, so the total number of edges is still small. And the latency is going to be logarithmic, which is actually the smallest possible. Okay. Unless if you bound the degree, that's the smallest possible. Okay. So binary tree is good for 1 and 2. Okay. And if I allow you to put more edges, you can make it a little more robust, but still it's not as fault tolerant. In what sense is it not fault tolerant? Can you think of example where it's really badly fault tolerant? Exactly. So, if this node fails, then, or an edge fails, let's say failures occur even along edges or node, they can occur either way. Then you're basically cutting out one half from the other half, right? So we don't want this property that, somehow if I cut one edge, the graph splits into 2 pieces, which are both very big. I don't want to have such a big disconnectivity just from dropping a few edges. All right. So fault tolerance is bad. In some sense, if I drop, let's say I tell you 3 edges get disconnected somewhere in the graph, then it could be that a vertex gets disconnected because all of my neighbors are disconnected, right? but I don't want that to disconnect the entire graph, right? If a node fails, I don't want my whole graph to get disconnected. If 10 nodes fail also, I want the remaining things to kind of be connected to each other. Okay, for the most part. Maybe the 10 nodes that failed are my neighbors, so those are gone. But other than that, I should say most of the stuff is connected. Okay, does it make sense? So, how can I ensure this? Well, this is what an expander graph is. So there's a combinatorial notion of an expander. Okay, so you want a graph G vertex n, let's say it's deregular again. Such that for every set S, if I take this set of vertices S, then in the binary tree, what happened is that there are big sets where the only outside connectivity is through a small number of edges. Okay, it's like saying, I have LA's network, LA is well connected, but if LA only has one outgoing edge to the rest of the US, then that's very brittle, because if that gets severed, then we are disconnected from the rest of the network, right? But if you have 1 million people here or something like that, you would want much more reliability coming out of this subset of vertices, right? Which binary tree did not satisfy, right? So we can quantify this by saying how many edges leave this set. Okay. The number of edges, let me call this okay, this is S complement. Okay. The number of edges with one endpoint in S and one endpoint in S bar should ideally be some constant times the degree times the smaller of the two sides. It's saying, you know what, S is very big, then almost half the edges, or 0.10% of the edges actually go out of it. And I want this to be true for every set, not just like one particular set, but every set. If the set is big, to disconnect it from the rest, I need to cut a lot of edges. Okay, this also implies in particular that to disconnect the graph, you need many, many, many nodes to fail, not just like a single node failing and so on. Okay, or to split the graph into two big disconnected pieces, you need many nodes to fail. If one node fails, 10 nodes fail, you're not going to have two big disconnected pieces. Okay, extremely fault-tolerant networks would satisfy this. Okay, now we would like to put all of the three things together. First, in fact, this implies low latency. That's something very cool, that this already implies low latency. Okay, because every time I have constant fraction of edges going out, you can easily show that the longest shortest path is logarithmic in this graph. Okay, so this you need, but you also need the degree to be small. If you take the complete graph, this is clearly true, but then I'm just putting direct connection between any two vertices. Okay. And here's a key lemma that was shown long ago because it has its origins in differential geometry as well. So if G is a ND half graph, if the second largest eigenvalue is at most lambda, then it is a combinatorial expander. Okay. So, I mean, initially I said, okay, small lambda means the graph is well connected, but this is actually saying you're well connected in this very, very strong sense that take any subset. If I take 10% of the graph, then a lot of edges are actually going up, and so on and so forth. Okay. All right. And so this means that having these graphs which have small degree and small lambda would be very nice. And if you were to build a network from scratch, that's the ideal network that you can build, right? I want a graph which has many, many vertices. Let's say I'm building a network on 10 to the 7 things, right? I want degree to be very small, maybe degree 4, degree 5, but I want it to be a combinatorial expander. Then what do? I can build an expander graph and then use that to lay out the connections, okay? So, and so, I mean, you should think of expander graphs really as extremely well-connected graphs with few edges. For example, can I have a graph which has 10 to the 7 vertices, and let's say maybe degree is 16 and lambda is half? Do such graphs exist? If they exist, then those are amazing for putting down networks, connecting road networks, or whatever you want, okay? Because they're extremely fault tolerant. To disconnect, you need to basically throw out almost a constant fraction of the vertices, constant fraction of the edges. The degree is very small, the latency will be very small, and so on, okay? So Leslie Valiant in the 70s asked this question. He asked, okay, can I get such graphs where the degree is small, but they're extremely well connected? He was even interested only in the combinatorial part. But the number of vertices keeps on growing. I could construct something on 16 vertices, but I want something on 10 to the 7, 100,000, whatever. Do these graphs always exist? Okay. And Pippenger in the 70s again showed they exist. Okay, showed that these graphs exist, but he did not give like an algorithm or a way to find these graphs. Because if you want to use it for some things, then I need to know what this adjacency matrix is, can I lay down this network, and so on, right? And then a big breakthrough for this happened due to Margulies from the 70s, who used number theory to construct such graphs. In particular, he used some really important theorem in number theory called Selberg's trace theorem, which has several Fields medals associated with it to construct such graphs. Okay, so it seemed like somehow you have to use extremely fancy number theory or something like that to construct such graphs. I mean, the definition of the graph is very simple, but to show that it's an expander has this property turned out to require some deep theorems for number theory. And that was the state for a long time. People kept on trying to construct these graphs explicitly, but the best things that we had were from number theory, okay? Until zigzag products came along. So this is Reingold, Vadan, and Wigderson. In 2001, they said we can use zigzag to construct expanders. In fact, we can do this without any number theory. And super efficiently. There is one other combinatorial construction between due to Miklos Aitai, but that was not very efficient. It was polynomial time, but it was not as efficient as zigzag. Okay. And the idea that they had was, okay, we have zigzag. So start with a small expander. Okay, I said it's the whole thing is that we don't know how to construct expanders on increasing number of vertices. If you ask me to construct an expander graph on 10 vertices, I can do it. If you ask me to do on 16 vertices, I can do it. But then you ask me to construct on 1,000,000, then I'm stuck. Or I have to use this fancy number theory. Okay. But they just said, start with a small expander H. Okay. And then some other small expander G0, and then take GK to be the same recurrence that we have. That's it. Okay. So I started with a small expander. This is also an expander. The new graph will have more vertices. The degree is still bounded because it's only coming from H. And it'll still be an expander, meaning lambda is bounded away from 1. Okay. And you can, if you're very clever with this recursion, you can make it so that edge computation only takes polylog time, not even linear time. Polylog time per each edge. Okay. That's why I said you can generate expander graphs on billion vertices, degree 17 or degree 20, whatever you want, in like a fraction of a second using zigzag product. Okay. And I only motivated expanders from this notion of like networking, but I said they keep showing up in many, many other places. This sort of very fault tolerant nature is very useful in many places. Okay. And zigzag product gave a very nice and probably the best combinatorial way to construct expanders. Okay. All right. So let me stop with that. And when we start on Wednesday, we will start a new problem, but we'll still work in the space of spectral graph theory. Okay, it's only 2 lectures. It's I would say it's not as impactful a result as ST-Canadian log space because it had many downstream applications, like knowing expander graphs, having the ability to construct expander graphs, universal traversal sequences, and so on. All of those came out of zigzag product. The next thing we'll see kind of a standalone thing, but it's very clever and also shows how you can reason about graphs in surprising ways using their spectrum. Okay. All right. I'll see you all on Wednesday again.
Hey, Professor, I had a quick question, if you don't mind.
Is there a question?
Yeah, I had a quick question, if you don't mind.
Sure.
Yeah, so my one question was in this right here on screen.
One second, actually.
Oh, yeah.
Stop the recording. Yeah.
Oh, sure.